Our last talk for the morning is Dr. Shaoyun Bai from the Simons Center, and he's going to tell us about twisted Shklyarov pairings and applications.
Okay, so thanks for the introduction and thanks for the invitation. I'm very happy to speak here. So I think I joined a few times, so sorry for the title. I just realized it. And what we're talk about today is based on the work in progress of Paul Seidel. So let me get started. So the talk is divided into 3 parts. So in the first part, I'm going to talk about the PQFT aspect of again we're talking about today, but it works out in a simple model. And in the second part, I'm going to talk about lattice fibrations and how to apply the PQFT perspective in the first part to solve problems in the second part. In the third part of this talk, I'm going to talk about some applications, which is of classical plate. So let me get started. So the first topic is about fixed point homology, which is a kind of application of the Lefschetz number of a homology from manifold. So in our setting, we're going to look at a closed monotone symplectic manifold. In other words, the cohomology class represented by the form is equal to the first string class of the manifold. So I choose normalization to make its constant being 1. You can always rescale the form to make sure that this condition is true for any monotone manifold in a classical sense. Then let's take a syntactic homomorphism of our manifold. In other words, it is a different homomorphism which pulls back the syntactic form of itself. And for simplicity of our discussion, let's assume that this homomorphism is actually non-degenerate, in the sense that if we take any fixed point of our so-called homomorphism, and we can look at linearization of this map at fixed point x, it doesn't have 1 as an eigenvalue. In particular, all the fixed points are isolated, and because compactness is on, there are only finitely fixed points of our syntactic homomorphism. Because of that, we can look at some kind of chain complex, which is so in this talk, we're going to work over C. So it's a complex vector space, we can see how to grade it, really generated by the fixed points of H. So the Zeeman gradient here comes from the sign of its determinant in the previous line. So to define clarity, really need to choose some kind of almost complex structure. So in this setting, we need to choose the one parameter family of almost complex structures parameterized by P. So P is in R, such that it satisfies some kind of specific periodic condition. So if you shift the time by 1, if you shift it back by the pullback of P, it will give us back JT. Then we can count for Morphic mass to our manifold with suitable conditions. So here, in this convention, I write U become over the domain R. 2, it has 2 coordinates as an P. So P is a variable corresponding to the variable we done before, and it satisfies the condition that, well, it's simply it has some kind of periodic condition, but still the twisting by P, and also it solves the multi-curve equation. And of course, we prescribe some kind of asymptotic condition and affinity to really define the incidence coefficients of our differential. Alternatively, you can view this as some kind of map become over a cylinder, but on the cylinder, there's some kind of twisting which you can kind of open, but along that kind of line where the cylinder open, there's a twisting inverted here, which is driven by P. Then, as usual in Floer theory, the output would give us some kind of Floer cohomology, and it's independent of the choice of almost complex structure and the pseudo observations of our syntactic homomorphism. It is an invariant of the map sheet. Okay, so it's a simple setup. So, as we know from his homology, this closed to infer homology groups have some arbitrary structures. It's also the case for fixed point infer homology. And for the purpose of this talk, I'm going to focus on 2 aspects of that. Firstly, it's called concrete area. In other words, what we do is we can define some kind of bilinear map with domain given by the tensor product of first homology of P, and the third homology is inverse. And it targets given by C, because work over C is a pair that is non-degenerate, and it has a property that A of P is the identity map, or actually the observation of that. Looking at the version of that, this recovers the concrete area on homology. So to define this thing, what you do is you take a cylinder as a definition for a differential. Imagine that if you're seeing that you kind of open the twisting exerted there given by P, and we could bend the cylinder over so that the boundary are oriented in different ways. So if you try to read the correct monogamy in the correct direction, one boundary component will give you phi, and the other will give you phi inverse. And what you do is you consider a simple synthetic vibration over the cylinder, and you count the perfect sections with the correct index. That will give you this kind of pair. On the other hand, there's something called conjugation isomorphism. So if the C is another symplectic automorphism, then there are isomorphisms between the fixed point homology of phi and the conjugation of phi acted on by the C. So to define this, the point is, if you have a fixed point of phi, if you apply the C to that fixed point, let's say it's the Cx, then it's a fixed point on the right hand side. And you then can use this correspondence to prove that the Floer data you already have on the Floer quotient complex of phi to define the Floer quotient complex associated with the conjugation. In particular, if our C here is actually given by phi, and our phi here is actually criticized as arc power, this kind of conjugation actually induces the Z0 R action. Of course, there's something to prove here. You need to prove that self-conjugation is actually driven by object identity, and that's an exercise to do. Okay, so here are the object structures on the Poincare homology. Okay, so this is the closed string part. So now let me move to the open string part. So I'm going to define the notion of twisted Shklyarov pair, and before that, we need to do some kind of preparation. So let me use the symbol F to denote a strictly proper infinity category defined over the complex numbers, and that we assume that it's also not too graded. So here, strictly proper means that if you have any pair of objects in the category, we take this common space. This will be a finite dimensional multivariate vector space over C. So of course, in general, in reality, it's more likely that we'll deal with infinite categories and homology are finite dimensional vector spaces. You can always use the linear lemma and go with the strictly proper case if you just assume the commodity problem. And okay, as a counterpart of the symplectic automorphism on the category, we are considering strict infinity automorphisms. I'll use also the same letter for phi, capitalized to denote such a map. So what does it mean? It means that it's an infinity functor. It's strict in the sense that all the higher maps included here, namely phi k with k at least 2, all vanish. And because it's an automorphism by assumption, to put here is phi 1 in the isomorphism of graded vector spaces, and it commutes with a differential. So of course, you might criticize this might be a pretty strong assumption to put on an infinity automorphism, but in reality, you can always enlarge your category to introduce more objects, so that this new category is isomorphic to the previous one we already had, and the induced automorphism on the second category is a strict infinity automorphism. So for example, to relate to the stories we just saw before, F here would actually be the monotone category of our monotones in canonical, where the objects are given the monotone Lagranges. It is a strictly proper category because we always refer to our parent Lagranges to make sure that they intersect transversely at 29 points. And for the automorphism, what we do is, because we have a symplectic automorphism phi, it induces a map on the entire category. And that's going to be the automorphism of our category F. And as I said before, it can be made into a strict automorphism by strictly enlarging our category, but without really changing the other behaviors of our category. Okay, so that's the setup. So we have in the category, we have automorphism. So from that, we can construct some kind of open string analog of the fixed point homology. That's called twisted functional homology. So let me write down the chain complex which is underlying this homology theory. So what we do is, so the notation for that is given by CC lower star as phi. So it's more or less the standard R complex the definition of Hochschild homology or Hochschild chain complex. So what we do is we take, say, K plus 1 tuple of objects indexed by L0 to Lk, and so let's read from right to left. In the first coordinate here, what we do is we insert the automorphism phi to the first component of this kind of top space. And for other components, we just take the top spaces in the infinity category. So more generally, you can replace the phi here by any infinity bimodule over the infinity category F, and you can simply write down the chain complex underlying the twisted homology coefficients given by this bimodule, but at expense of replacing the first coordinate as really from right to left by the top space of the bimodule. So that's the chain complex. And now we need to define differentials on this chain complex. So it's more or less the same as the differential on non-twist version of Hochschild homology. We just take the bar differential there. And one interesting feature of that is because of our assumption that our automorphism phi is actually strict, we only need to use structural coefficients of the infinite category to define differentials. Okay, so here's the statement which is, well, let me say it first. So it says the following. So let's assume that the category F is homologically smooth. In other words, the diagonal bimodule is a perfectly bimodule, or in other words, the diagonal is simply generated by tensor product between the right and left modules. Under this assumption, well, maybe let me put things away to be more precise. So as long as our category is proper, we can always find such a pairing defined over the tensor product of the Hochschild homology, twisted Hochschild homology with phi, tensored with the Hochschild homology with phi inverse. And if F is homologically smooth, this pairing is non-degenerate. So from the very artificial point of view, as you can see from this statement, because we view twisted Hochschild homology as an open string counterpart of fixed point vertical homology, this pairing should replace the concrete pairing, as in the case of Hochschild homology. So that's the first part of this statement. The second part says that if you consider Hochschild homology coefficients given by q to the power r, it actually emits a z mod r action, which is generated by conjugation with phi. So what I mean by that, if we go back to the second line here, we have this kind of R complex. Let's just apply phi to every column spaces listed there. And then we're just re-indexing the objects L0 to Lk to be phi L0 up to phi Lk. You can see that this also produces a Hochschild chain. So that's the given conjugation action on the Hochschild chain complex. And we can prove that the self-conjugation is actually changing the object identity. So that's why it has a z mod r action. Okay, so here's a statement about some algebraic properties, algebraic structures that exist on twisted Hochschild homology. And let me say that this pairing generalizes the pairing defined by Shklyarov for the case where phi equals identity. Okay, so let me just comment on how to really construct such a pairing and how to prove its non-degeneracy, but without really going into the proof. So from a high-level point of view, the construction of that relies on using a diagonal bimodule to construct an element inside here. So in the case where phi is identity, the point of view to take it is the concrete pairing, say on the cohomology closed manifold, is equivalently encoding information how to resolve a diagonal in the product as a tensor product of some of concrete dual basis. So you can always you can also do this in construction after inserting automorphism. So that will more or less produces kind of dual class, which more or less represents the pairing on the twisted version. And to prove non-degeneracy is actually based on generalization of a snake relation. I think TPFT, standard TPFT, but with the presence of the automorphism. Okay, so instead of really talking about abstract formulations, let's just write down an explicit formula for the twisted Shklyarov pair. So this is a chain level construction, and the domain of that is the tensor product of Hochschild chain complexes. So here, let's just write a Hochschild chain as, say, the form A0 tensor up to AN, and also B0 tensor up to BN. So what we do is, if you see the formula here, firstly, it's a super space. It's some kind of endomorphism acting on some kind of graded vector space, and we take the super trace of that. And what is this endomorphism? It's given by some kind of multiplication using the structural coefficient, structural mass in the infinity category. So we need to apply this kind of multiplication twice. As you can see, there's this kind of mu A appears twice. Okay, I think A should be F. So sorry for the inconsistency in notation. And if you see the left side of the A coordinates, we need to apply some suitable cyclic rotation. And for those ones which are on the right to A0, we apply the automorphism phi. Similarly, for the B coordinates, we also need to apply some kind of cyclic rotation. And for those ones which are on the left to B0, we apply phi. So this is the formula. It's kind of annoying if you see it for the first time. So let me just write down a special case of this formula, which is for the Hochschild chains of length 1. So let's take a pair of objects L0 and L1 in our category F. And F phi L0 would be this kind of length 1 Hochschild chain complex, length 1 part of Hochschild chain complex. Similarly, for F phi inverse L1 is the length 1 part of the twisted Hochschild chain complex associated with phi inverse. And then this super trace is defined over, is taken over the Hom space from L0 to L1. So what we do is, so let's look at the formula here. So we need to apply the mu2 in the bracket first. If we apply phi to y, we would obtain an element in the Hom space from phi L0 to phi L1. And let's look at B0. If we apply phi to that, that will give us element in the Hom space from L1 to phi L1. So in particular, they can compose with each other using the mu2 map. And if you, this is explained the mu2 inside the bracket, and there's mu2 outside the bracket. So let's take the multiplication of the output for the first multiplication with A0. And you can check that indeed the output sits inside the Hom space from L0 to L1. So this is the formula in the special case. And let me draw a picture to tell you the underlying geometric construction. So you should, so we have a pair of disks, which if you put some of them together, will look like some kind of annulus. So what we do is the upper disk characterizes this kind of multiplication inside this bracket. So to really read this picture, you should start from the middle right. You see super trace as matching with y. So, sorry, I think I said the wrong thing. So we should really start from the lower part of this kind of picture. So let's take the y and set insert y over there. And downstairs here, we apply the infinity structural maps to a bunch of elements from Hom spaces in the infinity category. So that will give us an output on the left part, lower left part of this picture. And let's take that output and do some further multiplication with elements on indexed by A. And that will give the output going back to the right part's picture. And to get super trace, we want the matching condition. So then we just sum these things up. That will give us this kind of super trace or twisted Shklyarov pair. Okay. So that's a pictorial description. Okay, so for the third part of the first part, we need to relate the closed string construction in the first part and the open string construction in the second part. So, and this is done via the twisted open closed string map. And here's the statement. So let's take our AFD category to actually be the monotone category of M, and let phi be our symplectic automorphism, and let big phi be its induced strict into the automorphism on category F. Then the statement is there exists a twisted open closed string map going from the Hochschild twisted Hochschild homology associated phi to the fixed point homology associated small phi. So the first part of this assertion says the existence of such a chain map. Second part says that actually we have to consider the diagram the following form. So it says the following. So to start with, we look at the tensor product of HHFB and HHFB inverse. So for this kind of vertical arrow, what we do is we respectively apply the twisted open closed map of phi and phi inverse to the two components. So they will land in the tensor product of the Floer cohomology of phi and phi inverse. And on these two tensor products, we've seen that there are pairs defined on them. So on the Hochschild part, there's a twisted Shklyarov pairing. On the Floer cohomology part, there's a Poincare pairing. And the point is, the open closed map actually preserved the pairing almost as defined before. Okay, so here's a corollary, which is an algebraic exercise. If F is homologically smooth, in other words, then we imply that the Shklyarov pair is non-degenerate, then the open closed map is actually injective. You can construct some kind of one-side inverse of open closed map from this diagram. You can show that injective. And to really prove that we have such a identification of pairings on the open closed map, if you're familiar with this story, it's actually a result of some kind of TQFT picture where you could think about a degeneration of some families of homomorphic analogue. So in the upper part of this picture, that's this kind of homology you want to construct. So interpolate between the Shklyarov pairing and the Poincare pairing. And of course, there are some other components of the boundary strata of the modern space, the boundary of the modern space, which corresponding to sort of Floer differentials, but let me ignore that. So these two kinds of degeneration, as written in the lower part of this picture, corresponding to on the left part, where this kind of conformal parameter associated to the annulus goes to infinity. And for the right part here, it corresponds to the degeneration of the annulus, where this conformal parameter is going to 0. So on the left part, because we have this kind of stretching, we will actually visualize this kind of open closed map. On the right part, because it is kind of pinching along the boundary, along this kind of with this pinching behavior, we will see the twisted Shklyarov pairing, and this picture actually appeared before. Okay. So here is a pictorial proof of this conductivity of the diagram. And let me say a few more remarks about this twisted open closed map before I move on to the next part. So I just talked about the non-degeneracy of the pairing and the compatibility of the pairing. I haven't said anything about this kind of Zeeman-R action, and but as expected, this twisted open closed map is actually Zeeman-R equivariant if our symplectic automorphism is given by the power of phi. And in the case where we're studying monotones, symplectic monotones, we know that on quantum homology, there is a quantum product with the first term class, which allows us to compose a quantum homology in smaller pieces. And this could be lifted to the categorical counterpart by looking at Lagrangians with this potential given by suitable value. So that will also give us a decomposition of the category. And the second remark to say here is the algebraic structures which slide before is more or less compatible with this kind of decomposition of both the closed string part and open string part. And there's an interesting question if you care about Lagrangian Floer theory. We can try to replace this kind of insertion of homomorphism by homological correspondence. Okay, so that's the first part. Is there any question? Okay. So in the next part, I'm going to talk about Lefschetz fibrations. And as the structure in the first part, we also started with the closed string counterpart at the start. So when I say Lefschetz vibration, I mean it's an exact sympathetic Lefschetz vibration in the sense that we can define parallel transport away from critical values, and near critical points, this projection map pi is modeled on the standard homomorphic Morse function, which is kind of the quadratic form. And it's exact in particular on the fibers valuable domains. So if we take a large circle surrounding the origin in the complex plane C, we can do the parallel transport once along that. That will give us the global monogamy in the fiber valuable domain F. And in some conventions, if we redefine Lefschetz fibrations in a careful way, this will be a complex supported exact sympathetic homomorphism. Exact means that if we compare the difference pullback of the real one form with the real one form, that will give us some kind of differential of a function, which is also complex supported. So that's the homomorphism we get on the fiber. On the photo space, what we look at is actually full rotation. What we do is we look at Hamiltonian, which takes the complex coordinate z to pi times the square of its modulus. And if you look at the associated Hamiltonian vector field, if you look at time one lap, it exactly rotates the plane once around the origin. And we compose this map with the projection map pi, we would get a Hamiltonian defined on the total space of this Lefschetz vibration. And of course, we have many reasons to care about that. And okay, it's just this what I said before. So of course, the question is how do we define some version of Hamiltonian Floer homology of the full rotation of the Lefschetz vibration? So the problem is if we just naively define that, there are, in a case, let's say the monogamy is identity, there is a family of fixed points in infinity which are not isolated. So of course, we need to do some perturbations to perturb those fixed points away. So traditionally, what we do is we do some kind of small perturbation using this rotation. So to be more precise, what we do is we look at the function which is epsilon x on z squared, and we use a lift of that to perturb the rotation Hamiltonian to remove the fixed points at infinity. But there are some other symmetries we can use on the complex plane. For example, we could look at Hamiltonian, which is actually some kind of non-zero number, real number, times the real part of our complex coordinate C. So in other words, if you look at Hamiltonian vector field associated with that, and look at the associated flow, that will more or less translate the plane in some direction. So because of the flexibility for multiple choices of observations, we could define different versions of Hamiltonian Floer homology. So let me use these notations. So for HF E1, it means we take the Hamiltonian Floer homology associated with Hamiltonian perturbed by this translation. And for the Hamiltonian Floer homology with this kind of number 1 plus minus 1 over 2. So 1 over 2 is some number between 1 and 0, so it could be anything. So it's the Hamiltonian constructed by perturbing the rotation Hamiltonian with this kind of small rotation perturbation. So why am I defining this? The interesting thing is the following statement. There's a pair of long sequences sort of relating Hamiltonian Floer homology in total space with the fixed point Floer homology of the monogamy acting on the fiber. So to be more precise, if we start with the rotation perturbation given by minus 1 over 2 times z squared, it makes some kind of map into HE1 so that the mapping cone of this chain complex computes the fixed point homology of the monodromy acting on the fiber. So if instead we perturb the rotation Hamiltonian by the rotation of the form 1/2 is like -1/2, it receives a map from H at E1, and on the chain level, if it takes the mapping cone, that also computes the fixed point homology of the fiber. Okay, so now we define Hamiltonian third homology groups, and now let's try to see some other algebraic structures on that. But before we do that, let me say something more. So I just talked about rotating the complex plane once by this rotation Hamiltonian, and we could try to integrate this kind of rotation to get something more interesting. So to be more precise, we consider Hamiltonian, which is R times the rotation Hamiltonian, where R is an integer. And we can consider similarly the Floer homology groups associated with different perturbations. So for H and ER, we use the translation of the third Hamiltonian to remove fixed points and infinity. And for this R plus -1/2, we take rotation Hamiltonian to remove fixed points and infinity. And as expected, they also fit into some longer sequences. But here, because we are taking iterations of the rotation, we would get the fixed point homology of iterations of the monodromy of fiber. All right. So in the monotone case, we've seen that there is a non-degenerate grid area defined over the fixed point homology, and the Pauling proposition says that the same is true for this kind of Hamiltonian homology indexed by integers. So if we take the third homology of R and third homology minus R, there exists a non-degenerate area defined only as a tensor product. And if we try to consider this kind of Z mod R action, as we've seen before, the second part of the statement says that there is also the Z mod R action defined on the third homology. And if we go back to the one-back sequence, as written down there, this kind of map from HFER to the fixed point homology of mu R is actually Z mod R. So this is about the close ring counterpart of the construction in this Lefschetz fibrations. Okay, so let me move to the open string counterpart. So because we're talking about Lefschetz fibrations, let's look at the Paul category associated with this Lefschetz fibration. So there are different conventions to define this category, but for us, we're just going to take the category such that the objects are given by all Lefschetz symbols. So here's a Floer proposition. I think the Floer statement is this kind of monodromy corresponding to Serre functor. But to be more precise, the statement is following. So let's consider the Hamiltonian diffeomorphism defined by the rotation Hamiltonian perturbed by this translation. Then this guy will induce an automorphism on the Paul Seidel category. And the point is, this induced automorphism is actually identified with the inverse Serre functor defined over the Paul Seidel category. So recall that the Serre functor could be characterized axiomatically using this kind of duality statement. And on the other hand, the Serre functor actually represents the linear dual bimodule, in a sense that if we insert the Serre functor on the first component of the diagonal bimodule, that will give us the linear dual bimodule, where here is a definition of the linear dual bimodule. So you more or less just take the dual of the Hopf spaces in the diagonal bimodule, and you dualize the structural maps back using this kind of pairing. Okay, so here we have an automorphism, which is a Serre functor, and we know that it is induced by this rotation Hamiltonian with a small perturbation. So And here is a statement relating this kind of further algebraic structures on the closed string on the part and open string on the part. It says the following: for any integer r, there exists a z-bar equivariant, so-called twisted open closed string map with domain given by the Hochschild homology with coefficients given by tensor product of the linear dual Y module with target given by the empirical homology of the R rotation with smooth rotation. And you can ignore the gradient shift here at the moment. So still this is about existence and equivariance. And the next part is about compatibility with the pair. So remember that the linear dual Y module is represented by the Serre functor, which is an homomorphism. So we can similarly define the twisted Hochschild homology for Serre functor, which is actually in this case Hochschild homology with this tensor product coefficients. And because it's an automorphism of the infinite category, we can define the twisted Shklyarov pairs as before, because the Gaussian category is proper. And this diagram is the same as before, which says that the open closed map is compatible with the pairing on both sides. So let me just comment on the proof and tell you maybe the difference or what was new here on the technical point of view. The point is in the monotone setting, homological curves are very easy to deal with. But for Lefschetz fibrations, because non-compactness caused by this kind of complex plane and maybe fiber, you need to find some other arguments to prove a priori C0 estimates. And that's actually the only new thing to be added in the case of Lefschetz fibration. And some kind of argument of this form already appeared in Seidel's non-listed papers, Lefschetz fibration and whatever. This part is written in four and okay. So the previous diagram says that the open closed map is compatible with pairing. But for that to be useful, for example, as we've seen before, if the proper category we have is homologically smooth, then the open closed map is actually injected. So to apply such a statement, we need to show that the Gaussian category is homologically smooth. So that's actually the case. And I mean, this is not really a new result. I think in the latest version of GPS2, they already have a proof of homological smoothness of Gaussian category, even if the fibers are different. So morally speaking, why it is true? The point is, if we choose a distinguished basis to define Gaussian category, this category will be directed. And as you might be familiar with Bennettson's resolution diagonal in the term category of En, this kind of exception collection gives us the resolution diagonal. And this more or less just uses directness of the objects we have. So we have some sort of automatic smoothness provided by the directed category. But if we just take a distinguished collection of vector symbols and let's say apply our simple automorphism given by this interfaces rotations, these objects are not necessarily preserved under such a rotation. So we have to take all vector symbols to really make sure that this functor could act on this category. So really the point of this proposition is to show that all vector symbols could be generated by the symbols from a distinguished basis. And as I said before, because this category is homologically smooth, then the open closed map is injected. So there's a long-standing conjecture of Seidel, maybe it was formulated more than 20 years ago, which says that this open closed map is actually an isomorphism. So the probability is half of that. Okay, so far everything is about homological curves, Floer open closed map, etc. And this is a conference on mirror symmetry, and let me tell you why this is of some kind of significance in a context with mirror symmetry. And that's going to be something about the notion of non-conductive anti-canonical devices. So what does it mean? So actually, it comes from a very innocent question. The question is following. So suppose that we have a category A, which is our set of categories, and how can we construct an infinite category B, for which the category A is included as a full subcategory? And using this inclusion functor, if we pull back the diagonal bimodule on B, and if we apply the quotient of this diagonal bimodule by the diagonal bimodule of orderly category A, this question asks that if you require that to be isomorphic to the linear dual bimodule with suitable shifting, how do we really construct such an infinite category from some kind of data? So let's just do things order by order. So on the level of morphisms, the thing we need to do is we just take the sum of the Hom spaces in A and Hom spaces encoded in the diagonal bimodule, the linear dual bimodule A dual. And the zeroth order information is contained in the structural maps in the infinity category and the infinity bimodule. Okay, so that's the zeroth order information. And now let's try to understand the first order information encoded in such an extension problem. So what we want is the input, we just have one input given by from the linear dual bimodule A dual. The output actually lands inside the diagonal bimodule A. So in other words, these maps could be assembled into map theta, whose domain is defined over the tensor product of A with the bigger shifting tensor with A dual tensor with this Floer tensor. And if you check this kind of mu square equal to 0 relation on the infinite category, you will conclude that this theta is actually a bimodule morphism which is closed. So in other words, this will define a class in H0 in the Hom as Hom in the category of bimodules from A dual with bigger shifting to A. And as I mentioned before, the linear dual bimodule is represented by the Serre functor. So if you do some kind of isomorphism, you will see that this class actually lands inside the Hochschild homology of A with coefficients given by the inverse Serre functor. And if you iterate on this kind of construction, you will actually conclude that the higher order information is actually contained inside this kind of Hochschild homology with coefficients inside iterations in inverse Serre homology, but it actually lands in the equivariant part. So this is a theory works in characteristic 0. Okay, so this is the question. And this is some kind of initial attempt to tackle this question. So, because of the preparations, here this proposition makes sense. It says the following. So, if this kind of twisted Hochschild homology, which look at this z mod r plus 1 invariant part, let's say they are supported on negative degrees, then an infinite structure on their sum as say Hom spaces of A and the dual bimodule A dual is uniquely determined by the first order infinite. And because we know that in algebraic geometry, the Serre functor on their category is represented by the tensor product with a canonical bundle with bigger shifting, so the inverse Serre functor is represented by the tensor product with the canonical line bundle. And such an element theta, then the twisted Hochschild homology, and because of the analogy I said, because of this kind of motivation from algebraic geometry, this theta can be viewed as a section of the anticanonical line bundle. And that's why we have the notion of non-commuted anticanonical divisor. Okay, so the main takeout from this proposition is if this kind of Hochschild homology is non-negative, is supported on non-negative degrees, the deformation problem, this extension problem we want to solve is quite simple. And the previous preparations actually tell you that this is the case for lattice vibrations. It says the following. So if we consider a lattice vibration, which is constructed by removing the fiber over infinity of an anti-canonical lattice distance. So in other words, we take some kind of funnel, smooth funnel manifold, and let's take a pair of sections, or generic sections, in the anti-canonical linear system, and let's construct a tensor out of that, and let's remove the fiber over infinity to construct such an exact symplectic lattice vibration. Then in this special setting, the Floer cohomology associated with Hamiltonian R, which replace the plane for R times with the small translation, is actually supported on non-magnetic degrees. And we know that this open close map is injected. We know that the Hochschild homology of such a guy is also supported on non-magnetic degrees. I also said that this open close map is actually Zeeman R invariant. So if we put over char 0 and pass to the invariant part of this group action, we conclude that indeed the Zeeman R+1 invariant part of each lower star A S minus R+1 specifies the desired property in the composition. So the deformation problem, this extension problem is quite simple because we just need to use the first order information. So this about non-kinetic geometry is little input from simple geometry. So what would be some implications on mirror symmetry? Well, the point is, let's still assume that this vibration is anti-canonical. Then that B actually be the category, the compact category of the fiber. Then if you consider the restriction factor from the Seidel category to the compact category of the fiber, well, this more or less defines a non-committed anti-canonical divisor as worked out in another paper, Seidel papers, so this time 6. And because in this setting, to recover B from A, we just need the first order information. So this is the equivalent formulation of this kind of first order information. What we do is we just need to choose some kind of distinguished natural transformation from the third factor to identity factor. And under open close open map, it corresponds to the identity element in HIE1. So what I said before, not only works in the exact setting, but also works in the non-exact setting. So the construction here to do is, if you look at an anti-canonical tensor cooked up out from some kind of final manifold, let's just blow up the base locus, and then we remove fiber over infinity. So here we will also get some kind of vibration, but here it's actually proper. The fibers are compact closed, clouding under surfaces. And this is interesting in homological mirror symmetry. And actually, this kind of deformation problem, extension problem, and open close map, etc., works in this non-exact setting. So in other words, we can also recover the category of the closed on the surface out from the Seidel category of this complication and some first order information encoded inside this natural transformation from third factor to identity. So with some other works, is actually a step towards showing that the compact category of a surface is actually defined over polynomial and after 5 years. So there's a huge conceptual jump here, but this is part of the thing which needed to prove this. Okay, so questions? Oh, okay. So let me give you another sample application, which is a classical flavor. So it's about isolated singularities. So let's say we have a homomorphic function f defined over Cn, such that the origin is an isolated singularity. And then we can look at this kind of analogy surrounding a small loop. Small loops surrounding the origin, and we could endow everything there with this synthetic structure, and that would give us some kind of monogamy, which actually defines an exact symptom homomorphism of the Miller plan. So there is a theorem of MacLean saying the following. So let M be the multiplicity of F at 0. Sorry, it's not n 0, it's at 0. So if we consider the iteration of the monogamy, and let's say that the power we take is less than the multiplicity of the singularity, then the fixed point homology of that vanishes. Okay. So it is proved using resolution singularities, but we just need a statement. So go back to the long exact sequence we've seen before. Is that they have the following implication. So know that if we choose this kind of, for any exact Wiggle domain, if we choose Hamiltonian or identity, which is, say, on the boundary, it is in a positive direction of boundary flow, they'll actually compute the cohomology of underlying space. So that's the case, also the case here. So in this long exact sequence, we have the cohomology of Cn, the third cohomology of this kind of rotation Hamiltonian, and the third cohomology of the monogamy. And because we know that the third cohomology of monogamy vanishes, we actually have an isomorphism from the cohomology of Cn. So it's not third cohomology of Cn to third cohomology of E. So it's a rank 1. So it's less than or equal to 1. On the other hand, we can try to morphify our homomorphic map to get well-behaved set of categories. And because we assume that 0 is a singularity, this category in particular is non-empty. So we know that the Hochschild cohomology of that is non-zero. And in this setting, the Hochschild cohomology is actually isomorphic to the Hochschild homology with coefficients given by inverse Serre function, and it's non-zero. So this guy has rank at least 1. And then using the interactivity of open closed map and compare the rank, we know that this guy is exactly one-dimensional, and Hochschild cohomology is also exactly one-dimensional. So the symmetry there is not so precise. It should be the Hochschild cohomology is one-dimensional, because the third cohomology will need to use open closed map. So this is a quite simple observation, but it has some interesting corollaries. So, for example, it's not about if you consider the homomorphic map taken over C star to the n to C, which is the standard mirror of CPN, it says that it cannot be deformed to a regular function with isolated singularities with fewer critical points. Sorry, fewer critical values. So, how do we prove that? So to prove that, we need to introduce some kind of intermediate invariant. So recall that the Hochschild cohomology actually has a ring structure. Because it has a ring structure, and let's say it's bidimensional, we can talk about the half-length of that. It's defined to be the following form. So let's say it's defined to be the maximum number R, such that we could find a sequence of elements inside Hochschild cohomology A1 up to AR. And of course, we would assume that they're one identity and they're actually nilpotent. And the condition to satisfy is their cup product is non-zero. So the maximum R such that such a non-vanishing property is true. Okay, so let's try to investigate its definition in this simple example. So homological mirror symmetry tells us that this Shklyarov category is actually equivalent to the pure category between sheaves on CPN. So my claim is the cup length of that is at least n. So why is that true? The point is, let's look at Hochschild cohomology, and by HKR theorem, we can identify that with the cohomology of homomorphic polyvector fields. And on Cn, there is a homomorphic C star to the n action. Let's simply take some kind of and tuples of linearly independent homological vector fields induced from the Caesar function. And let's take that kind of top product, and you can see that they don't really vanish. So we know that top length is bounded below by n. Okay, so that's the some computation using this simple form of homological mirror symmetry. Okay, so go back to our Shklyarov category. So let's assume that our Shklyarov category is actually the Shklyarov category associated with the Lefschetz fibration coming from a more sophistication of asymptotic singularity. So then I claim that the top length is 0. So why that true? Because we know the Hochschild homology is one-dimensional and has an identity. So there's no other maps to check. But no elements. So the top length is 0. So that's the second ingredient. For the third ingredient, we need to make use of semi-orthogonal decomposition provided that we could simplify the critical values. So the algebraic statement is following. Suppose that our infinite category A has a semi-orthogonal decomposition of the form A1 up to AN, in the sense that half from AJ to AI with J greater than I is 0. So then the top length of this whole category A is bounded from above by the sum of top lengths of AI with some kind of shift. So that's also some easy algebraic exercise. So remember that for this potential, we have exactly n+1 critical values. So if we could deform this function to a regular function with fewer critical values, near each critical value, we should still have some kind of isolated singularity. And if we perturb that locally near that kind of critical value, we can get this kind of local Shklyarov category. And they could give us some kind of simplified version of the semi-orthogonal decomposition of Caesar to the end without this potential. But that will give us a contradiction because each local piece would contribute to top length 0 on the right part of the inequality. And we know that the length, if the critical values could be collapsed with each other, this length of semi-orthogonal decomposition must be less than or equal to n+1. And that's a contradiction because we computed that the top length Hochschild homology of the category of computer sheets on CPN is bounded from below by n. And that's a contradiction. And so here is a sample application of some kind of result from Floer theory to some problem of a non-classical player. Okay, so I think that's good. Time to stop there.
Thank you. Question?
So could you please go back to the page titled Isolated Singularities?
I could. So is that all of your question?
Yeah. So
okay.
I remember that my team also that the space point for homology is also related to the homology of the arc space of the central fiber.
Yes, yes.
So I wonder, would it be possible to use this machinery to study the stringent Cauchy number of the central fiber, which is basically defined by the homology the arc space of the central fiber using this Floer homology technology. For example, can we prove the comparability of these?
Okay. So let me say things like this. Firstly, I think Mark announced this result a long time ago, but still I think there's something for him to work out. So that's not a result yet. But I totally believe he can do it. Secondly, I think maybe 2 years ago at some foundation in New York, actually Mark asked the question whether we could understand multiplic integration using Floer theory, and the answer is I don't know. And I think your question is fantastic, and